Hi everyone, I hope you can hear me. Let me know if I'm audible. Okay, let's just get started. Today we are going to start synchronization, right? Some of the questions from the synchronization. So, okay, can anyone please confirm if I'm audible? Cool. Those who are watching me first time, let me quickly introduce that I'm Sachin, and I have worked as an applied scientist at Amazon, and I have finished my masters from Indian Institute of Science (IISc), and I have achieved All India rank 33 in GATE, right? Okay. Let's just get started with our discussion today. So today we are going to discuss few of the topics which are mutual exclusion, progress, bounded waiting. I mean some of the synchronization method. So what are the requirement of the synchronization, right? And how we can achieve the synchronization. So these are the requirements that we want. And using semaphore we can achieve using some instruction called test and set, and like hardware supported instructions we can achieve, or maybe some software supported solution like Peterson solution also. Some kind of solution are there using which we can also achieve the synchronization, right? So anyway, let's just move further and let's just understand these terms. What are the mutual exclusion, what is progress, bounded waiting, and all, right? So mutual exclusion as it is revision class, so I'm just going through the revision slides quickly. Okay, if there is any issue, then you can let me know. Okay, great. So mutual exclusion is very easy to understand. It means that you do not allow two processes at the same time. Which means if there is a critical section, in that critical section, you do not allow two processes at the same time. That is what mutual exclusion says, right? Great. And what is this progress and what is bounded waiting? Let me just quickly revise you. So again, this is a revision session, most conceptual revision, which means here we will be just revising the topics, and I might not be telling everything in very good detail because I mean from very much basic, because I'm just revising few of the concept, and if some concept, if I feel that I should be I should be teaching in the detail, those concepts only we will be teaching in the detail, right? Okay. So what is a progress? Progress meaning in the layman terms is that like let's suppose there is a critical section and few processes, let's suppose P1, P2, P3 wants to enter in this critical section, right? Suppose these processes want to enter in the critical section. Then progress says that if in this critical section no one is there and someone wants to enter, then there should be some progress in this critical section, which means critical section should not be just ideal if someone wants to enter, right? So progress says that there should be some progress means that there should be some progress in the critical section. That's what progress says. There should be some progress in critical section. That's what progress says, right? Let me know if that is clear to everyone. Okay, so let's just move further. So that's what progress means, and like it is written exactly the same thing here. The purpose of this condition is to make sure that either some process is currently in the critical section. If some process is in the critical section, then anyway there is a progress in the critical section. If some process is not doing in the critical section, and if there is at least one process wants to enter in the critical section, then it will enter. It will enter and do some work. In both the cases some work is getting done. So progress means that some work should be getting done in the critical section, and therefore all processes are making progress overall, right? Okay. Now, what does this bounded waiting mean? Bounded waiting, in layman terms, it means that if let's suppose multiple processes wants to enter and P1 get a chance somehow to enter in the critical section, then P1 should not be re-entering, and P2 and P3 should not be just waiting, and then P1 cannot re-enter again. Which means that a process P is not bypassed by some other process P prime. That's what bounded waiting means, right? So bounded waiting says that a process should not be bypassed by some other process P prime. Let me know if that is clear to everyone or there is any doubt, right? So that's what bounded waiting means, that a process should not be bypassed. Okay. Now moving further. So, uh, like let me just give you one example. Let's suppose that there are few processes P1, P2, P3, and then let's suppose this P1 is getting a chance to enter, and then it should not re-enter. That's what this bounded waiting means, right? So interestingly, this bounded waiting does not say if a process can actually enter, which means that this bounded waiting does not say if a process can actually enter, which means that let's suppose that it might be the case that there are three processes that wants to enter in the critical section. This is critical section. There are three processes, P1, P2, P3, that wants to enter in the critical section, and then those three processes, all of them are blocked, right? Then also bounded waiting is satisfied. That's very interesting point, right? Then also bounded waiting is satisfied, although there is a deadlock. Although there is a deadlock, still bounded waiting is satisfied. Basically, bounded waiting just says that you should not bypass. Here, no one is bypassing, right? Tell me if P1 is bypassing P2 or P3, or maybe P2 is bypassing some P1 or P3. Anything is there? No, right? So since no one is bypassing, that's why I will say that bounded waiting is satisfied here. So that's very, very important and very, very interesting point, that even though there is a deadlock, there is a bounded waiting, right? Cool. Now, uh, can you tell me maybe a pseudo code that how we can have such situation? Maybe I can write a pseudo code. How? For P1 I will, or maybe for P1, P2, P3, for every process I will write a code which will say while true. I mean, I will let them stuck in this forever for loop, and then there is a critical section. No one is entering. Okay, in this case, no one is entering. Still, there is a bounded waiting that is satisfied. So bounded waiting is satisfied, and deadlock is also there, right? Now, basically, I will tell you the relationship between bounded waiting. Actually, there is no relationship. So, I will tell you the different cases where bounded waiting is satisfied and deadlock is there. Bounded waiting is satisfied, deadlock is not there. Bounded waiting and deadlock both are not satisfied, something like that. So, we will see different scenarios in just a few minutes. Let me know if this is clear to everyone. So here the bounded waiting is satisfied, and and the deadlock is still and the deadlock is there, right? Okay. Tell me, is there a progress? Is there a progress in this case? So suppose you have this case, let me know if the progress is satisfied. See, progress and deadlock are opposite to each other. If deadlock is there, then you cannot have a progress. So progress is not there because there is no progress in the critical section, right? Not there. Is this okay to everyone? Okay. Now let's just move further. Okay, continuing further. So a bounded waiting in layman terms means that no one should be bypassing. I mean, P should not be bypassed by some other process. That's what bounded waiting means. So here, no one is bypassing some other process, right? If there is a deadlock, then also bounded waiting can be satisfied. That's also very interesting point, right? Okay. Now let's move to different slide. So here in this case, deadlock is satisfied, but deadlock is there, but bounded waiting is also there. A bounded waiting is also satisfied. Now let's just see if progress and bounded waiting has any relation. First of all, like intuitively you can say there should not be any relation. Can anyone tell me why? Why I'm saying intuitively there should not be any relation? Because if at all there is a relation, which means if at all progress implies bounded waiting, or maybe bounded waiting implies progress, then I should not be having different conditions, right? I should just be having one out of those three conditions that I mentioned, mutual exclusion, progress, bounded waiting. If one imply another, then I should be just having one of them. Maybe, right? Why designers have these two conditions? Since there should not be any relation, I mean, no one implies, neither progress imply bounded waiting nor bounded waiting imply progress. That's why I do have these two different conditions, right? Okay. Anyway, let's just see it more clearly. So neither progress imply bounded waiting nor bounded waiting imply progress. Can you tell me any example where progress does not imply bounded waiting? Progress does not imply bounded waiting. I mean, progress is there. I want to have a condition where progress is there and bounded waiting is not there. Very easy, right? I mean, you can have a critical section. You can have a critical section where you can have a process P1, okay, and P1 is again and again entering, right? And then P2 and P3 are waiting for each other. Something like this, right? P2 and P3 are waiting for each other. So in this case, you will say progress is satisfied because in critical section some progress is there. But who is making that progress? That for that progress is not responsible for that. Like all of them should make progress or not. Bounded waiting says that no one should bypass me. But here you are bypassing. So that's why you will say bounded waiting is not satisfied and progress is satisfied. What about bounded waiting is satisfied? Let's suppose I want to have a condition where the bounded waiting is satisfied, but progress is not satisfied. Progress is not satisfied. Very easy, right? It is just a deadlock condition. I mean, everyone is stuck. If everyone is stuck, interestingly here, if everyone is stuck something like this, then interestingly, in case of deadlock, I mean, in this particular case, in case of deadlock, it is not always true that in case of deadlock, bounded waiting is satisfied. But in this case, I'm saying that here everyone is stuck, so bounded waiting is satisfied because no one is bypassing anyone, right? And progress is not satisfied because in critical section there is no progress that you are doing. Progress is not satisfied. Obviously, there should not be any relation between these two, right? Okay, yes, Deeptanshu, that is right. Okay, now let's move further. So see here, progress does not imply bounded waiting. Progress says that process can enter with a finite decision time. Okay, it does not say that which process can enter. So basically, the progress does not say about a particular process. I mean, here the P1 is making the process progress, P2 and P3 are not waiting a progress. Still, the progress is satisfied, right? Okay. So ultimately, I can say that progress and bounded waiting are independent of each other, right? That's very important point. That progress and bounded waiting are independent of each other. Now, if a progress is okay, let's just see some other term which is starvation freedom. Okay, what is this term? It says that if a process is trying to enter in the critical section, it will eventually enter, which means there is no starvation of any process. Now tell me, can you say that bounded waiting imply starvation freedom? Can you say this? If bounded waiting is there, then there is no starvation. Let me know if you can say something like this. No, right? See, we cannot make such a statement. Why? Because bounded waiting is satisfied in case of deadlock also. That's the problem, right? In case of deadlock also, bounded waiting is satisfied. So that's why I will say if bounded waiting is satisfied, then I don't know whether the starvation is there or not, because then deadlock might be there, right? If bounded waiting is satisfied, then maybe it is deadlock also. So starvation is not satisfied. So I cannot say that bounded waiting means that starvation it is starvation free, right? So this is false. I hope everyone understood this. Why? Because in case of bounded waiting, deadlock also could be there. So that's the main point, right? Okay. So does bounded waiting imply starvation freedom? Which means if there is a bounded waiting, which means you have bound on every process that no process should bypass anyone. Then everyone. Does it says that everyone will get a chance? Starvation freedom means everyone will get a chance. Everyone will get a chance in a finite time. If bounded waiting is satisfied, can I say that everyone will get a chance in finite time? So answer of this question is no, right? I cannot say. Why? Because if bounded waiting is there, then maybe it is deadlock. But yeah, definitely I can say bounded waiting plus no deadlock. If I just eliminate this deadlock condition, no deadlock, bounded waiting plus no deadlock, then yes, this is starvation freedom. Right? So this thing is true, but this is false. Is this understood to everyone? Okay, I hope that is fine, right? So in case of bounded waiting, if there is no deadlock, if I just eliminate that condition that deadlock could be there, then you will say yes, things are fine, right? Okay, I mean there is just starvation freedom. So no deadlock also mean like I will just tell you in just a couple of minutes. No deadlock means like progress and no deadlock are almost same. Okay, no deadlock and I mean system is not in deadlock, and it means that there is a progress. Okay, So I mean progress and no deadlock are almost same. I mean I will just clarify it in just couple of minutes. But yeah, so you will say that instead of no deadlock I'm writing it progress here. Okay, so I'm saying progress plus bounded waiting, or maybe no deadlock plus bounded waiting implies starvation freedom, imply to starvation freedom, right? Okay. Alone, bounded waiting cannot imply starvation freedom. Reason being is that bounded waiting does not say if a process can actually enter, which means there could be a deadlock also in case of bounded waiting, right? Okay. So now I hope you are getting. But why I'm writing progress is because like this. See, suppose if I say that there is a process P1 that is entering, and then like it can enter again and again. Okay. Yeah, anyway, let me just do one thing. Like I wanted to clarify the difference between bounded waiting, sorry, the progress and no deadlock. So let me do one thing. Let me just, spend a few more slides. Then I will just tell you the relation between progress and deadlock. Okay. Okay. So I hope that is fine. Till this point, this is fine. Now, do you see one very nice thing? What is very nice thing? This progress and bounded waiting. This combo is very nice, right? I mean, this combo is so nice that it is saying that things are starvation free. I mean, every process will get a chance, right? So if I have these two conditions, which is progress and bounded waiting, these two conditions are very nice conditions. Together, this combo is very nice combo. This combo is very nice, isn't it? So you will say that yes, this combo is very nice. So you will say that this combo, if I have this combo, then the starvation, my process are having a starvation freedom, right? Okay, okay. Deeptansu, is there any doubt here? I hope you understood, right? So now, on top of this, there is one more condition if we add. What is that condition? If there is one more condition that we add, which is a mutual exclusion. On top of that, if we add one more condition, which is called mutual exclusion, then this condition plus these two conditions are extremely nice, which means this condition mutual exclusion, it says that exactly one process, or maybe at most one process, you can say at most one process will be entering in the critical section at a time, and this combination will say that everyone will get a chance, right? So see, there is very nice combo of these three, which is mutual exclusion, progress, and bounded waiting, right? These two together says that okay, everyone will get a chance. These two together says that everyone, right? And this says that okay, at most one process can enter at a time, right? At most one process can enter at a time. So basically, these three conditions are very nice conditions, right? Which is saying in a critical section, at most one process can enter at a time. Okay, I mean, if multiple processes are basically trying for the critical section, then only one process will get through it. And it's not like that just one process can keep on coming in, and these are 4 hour waiting, because I do have these two conditions also. It means that if I do have these two conditions also, it means that everyone will get a chance. Currently, let's suppose it is getting a chance, but it doesn't mean that these three will not get a chance, right? So that's why these three conditions are very nice conditions. Okay. Now let's just move further. So now let's just see a relationship between deadlock and bounded waiting, which means can there be a case where deadlock is there but bounded waiting is not there? Can there be a case when deadlock is not there, bounded waiting is there? Can there be a case when deadlock is there and bounded waiting is also there? Okay. Let's just see these three things. So let me know if my slides are visible, right? I hope it is visible. Just a second. Okay, so I hope my slides are clearly visible, right? So let's just see if we can have some examples where deadlock is there and bounded waiting is not there, and deadlock is not there, bounded waiting is there, something like this, right? So let's just see maybe one example where the deadlock is there and bounded waiting is still satisfied. So can you see that example? I mean, that's one of the easiest example that we have been talking, right? What is that example? You can have a critical section where all of them are blocked. P1, P2, P1, P2 and P3, all of them are blocked. So you will say, since all of them are blocked, deadlock is there and bounded waiting is also satisfied, right? Now, let's just see a case where deadlock is not there. I mean, you do not have a deadlock, but bounded waiting is satisfied. That's also very nice case. I mean, this is same as saying that progress deadlock is almost same as the progress. Okay, deadlock is not there, which means progress is there. So basically, it means that progress is there and bounded waiting is also satisfied. So yeah, there are, if there is some nice solution, in that solution maybe you can have these things, right? Progress and bounded waiting both satisfied, right? Okay, I mean, maybe the Peterson solution is one of them. I mean, the progress and boundary waiting both are satisfied, and there are many solutions where progress and boundary waiting both are satisfied, right? Now let's just see a case where you have a deadlock, which means there is no progress and bounded waiting is also not there. Okay, so can you have a case where you have a deadlock and bounded waiting is not satisfied, which means that you are saying that everyone is in the deadlock, P1, P2, P3. I mean, no one can enter in the critical section, still the bounded waiting is not satisfied. It seems that if deadlock is there, then bounded waiting is satisfied, right? I mean, if no one can enter, then there is no point of bypassing something, which means that a process cannot bypass some other process. So, can you have a case where deadlock is there, which means everyone is stuck, right? Deadlock, whenever I'm saying deadlock, I mean that deadlock in a system. Deadlock in a system means all the processes are stuck, okay? And deadlock, see, sometimes I will say deadlock between two processes, which means this is making some progress or something, and these two are waiting for each other. So there's a deadlock between two processes. But if I'm saying just deadlock, then it means that deadlock in a system, everyone is stuck, and still I am saying that bounded waiting is not satisfied. Can you have such case? Answer is yes. Okay, let's just see that case. If where the deadlock is there and bounded waiting is also not satisfied. See, deadlock is there, which means everyone is stuck. Then what the why I am saying that no bounded waiting is not satisfied means that someone is bypassing, right? Bounded waiting not satisfied means someone is bypassing some other process. Let's just see, right? So maybe you can read this paragraph. Here the deadlock is satisfied and the bounded waiting is not satisfied, right? That paragraph I have taken from Stack Overflow. So I will give you one example, but optionally you can also read this paragraph. So basically now I am at this point where I want to make an example. I want to give you an example where the bounded waiting is not satisfied. I mean, deadlock is there, still the bounded waiting is not satisfied. Actually, it can happen if in a program in different execution that is possible, which means in one of the possible execution this might lead to deadlock, but in one of the possible execution the bounded waiting is not there. Let's just see that what do I mean by that. Consider this, okay? Consider this program. This is P1, this is P2, and this is a shared variable which is x equal to 0. Now here, let's suppose while x greater than 0, this is the code, this is the code for P1 and exactly same code I have for the P2. Tell me, is bounded waiting is satisfied here? Okay, this is semicolon. Tell me bounded waiting is satisfied here. X greater than 0, this is false, it will go here and then it can re-enter, right? If since it can re-enter, that's why bounded waiting is not satisfied. Definitely bounded waiting is not satisfied. Everyone agree with me? Everyone agree that bounded waiting is not satisfied in this case? Let me know if there is an issue, right? So now let's just see if if in this particular case deadlock is there or not. Okay, so can you have a deadlock? Can I have both the processes stuck at a same point? I mean, can I have both the processes stuck at this entry point? Can I have x greater than 0 for both the process? See, this is not, this is not bounded by the semaphore, so there will be a race condition. can I do one thing? Can I increment this x 2 times, right? I mean, I can increment this x 2 times and just decrement one time. That's very much possible, right? So basically x is initially 0 and let both the processes enter in the critical section. Mutual exclusion is also not there, but let's not worry about it. And then both the process incrementing x value. Now the x value is 2, right? Now x value is 2. Now can we just decrement one time? Obviously it is possible because of the race condition. So you can say that here the x value is 2 and then I will be decrementing. I mean, maybe you can nullify one of the process effect, right? I mean, I'm not going into the detail, but if there are multiple execution that you are doing, then you can actually nullify all of them. You can just have one of them, right? So you can just nullify this, and then you can say while the both the processes are coming out at that time, x is just 1. X is just 1. So which means at next time both processes are getting stuck in this loop, and that's why deadlock is also there, right? So in this case deadlock is also there and bounded waiting is also not satisfied. So that is why I will say that there are cases where deadlock is there, bounded waiting is not there, something like this. In fact, there is no relation between deadlock and bounded waiting. Okay, so there is no relation between deadlock and bounded waiting. First point is that. Second point, that I mean, bounded waiting and deadlock are not related, and deadlock and progress are very much related. If deadlock, then no progress, or maybe in fact you can think in contrapositive way, which means if progress, then deadlock cannot be there, no deadlock, right? So in short, bounded waiting and this deadlock are not related, but progress is very much related to the bounded waiting, no, to the deadlock, sorry. Okay, so I hope everyone understood these 2 points. Now let's just move further, right? Let's just move further. So everyone understood this. Basically, I mean, and there is no relation between the bounded waiting and progress also, right? Third point, that you know that there is no relation between bounded waiting and progress also. Okay. Now let's just see that how to solve questions, which means given a question, how to check whether mutual exclusion is there, how to check whether the progress is there. Progress, see, as I said, like progress means absence of deadlock, right? Progress and deadlock are very much related. Progress is there, then no deadlock, or maybe vice versa, that if deadlock is there, then no progress, something like that, right? So anyway, progress means absence of deadlock. So let's just see that how to solve questions, which means in a question, how to check whether mutual exclusion is satisfied, how to check whether progress is satisfied, how to check whether bounded waiting is satisfied, right? So that's very, very easy to check. To check mutual exclusion satisfied, what will I do? I will make one process in the critical section and another process I will see if that can enter in the critical section. So basically, let me just tell you how to check if mutual exclusion is satisfied or not. Okay, this is from the question's point of view. Given a question, how you will be checking. Sorry. So how to check if mutual exclusion is satisfied. So what will I do? Given a critical section, so there are two things I will be checking. Okay, first thing is that given a critical section, I will check if one process is in the critical section. Okay, then if another wants to enter, then I will check can P2 enter. If one is in the critical section, this is what I will checking. Also, I will make a scenario where I will be saying, okay, none of them is in critical section, both wants to enter. Okay, P1 and P2 both wants to enter. Then I will check if like how many processes it is basically allowing at a time, which means can both enter at the same time, right? Can both enter at the same time. So I will be checking can both enter. In both the cases, there is no mutual exclusion. Okay, so this is the first thing that I will be checking. This is the second thing. I will make one process in the critical section. I will ask can another one enter. If no, good, but that's not enough. Okay, I will also be checking this thing. I will say that okay, if both the processes wants to enter in the critical section at the same time or not, right? So these two things I will be checking. Okay, this is A and B. You can say this is A, this is B, this is A, B. Now for the progress, I will be checking two things. For the progress, I will be saying no process in the critical section and P1 arrives. It should get enter, which means, okay, let me just tell you how to check for progress. That is a critical section. Okay, if no one wants to enter, P1 arrives, then P1 should be allowed. Second point is saying two or more processes are in the entry code, show that at least one will enter, which means if two or more processes are in the entry code, then at least one should get enter. Okay, at least one should get enter here, at least one. And what does the mutual exclusion says? Mutual exclusion says that at most one should enter. If progress and mutual exclusion both are satisfied, it means that exactly one will enter, right? I mean, mutual exclusion does not say that there is a progress. It just says that okay, both processes cannot be at the same time. But if you also have the progress, then it means that exactly one will always enter, right? Because progress is saying that at least one enter. Mutual exclusion says that at most one enter. So progress and mutual exclusion both says that exactly one enter, right? And similarly, now if I have the bounded waiting, then it will say that that you will also enter. I mean, bounded waiting says that no one will bypass this. So bounded waiting is saying if P1, P2, P3, three processes are competing for this critical section, then let's suppose all of the conditions are satisfied, mutual exclusion, progress and bounded waiting. Mutual exclusion progress will say that exactly one will enter. And along with the bounded waiting, right? Along with the bounded waiting. So this is given by mutual exclusion plus progress. This will say that exactly one will enter. But if I do have the bounded waiting also, then this will say that okay, no one will starve, which means that this will also get enter. I mean, everyone will get a chance. So how to check for the bounded waiting? I will be making one of the process in the waiting area and one of the process in the critical section. Then I will check whether it can be bypassed or not. Okay, let's probably directly solve the questions. Then you will get to know. So let's solve this question. Let's check whether here. Okay, so let's suppose this is one question that I have, and let's check whether the mutual exclusion is satisfied, bounded waiting is satisfied, progress is satisfied. Let's check these three things. Tell me, so this is a semicolon that I have. Okay, so let's suppose the turn initially could be anything. Let's suppose turn is initially 0. Tell me if the mutual exclusion is satisfied. See, turn not equal to 0, which means either turn is 0 or turn is 1, right? Turn cannot be both at the same time. So that's why either this is true or this is true. So let's suppose if turn is 0, which means this is true, right? Turn not equal to 1. Basically, this is true, right? Because turn is 0, so turn is not equal to 1. So this is true. So that's why P1 will get stuck. So turn equal to 0 means that P0 will enter critical section. So it will enter critical section and it cannot enter. Can both enter at the same time, right? I mean, let's just check. Maybe like the moment it is leaving out, at that time turn is 1, right? In between turn cannot be 1, and it can enter only when the turn is 1. So that's why the mutual exclusion is definitely satisfied, because the turn is only one. Turn will take one of the value at one time, right? So that's why the mutual exclusion is satisfied. Let me know if there is any doubt to anyone. Shriram, is this clear to you? AP? Okay. So now let's just check whether the bounded waiting is satisfied or not. Bounded waiting says you make one of the processes in the critical section. Maybe let's suppose I'm making one of the process, which is let's suppose this P0 in the critical section, which means turn is initially 0 and P0 is here. Then can P0 go, which means turn it will make turn 1, right? And then can it go and come again? If turn is 1, then it will enter, right? Turn 1 means that it's a turn for the progress one, process 1. So it will enter. So P naught cannot go and come again. So that's why the bounded waiting is also satisfied. What is progress? Progress says that, again, progress says two things. It says that if both of the process, okay, so it says, see, progress says no process in the critical section, P1 arrives, then P1 should be able to enter, which means that suppose currently no process in the critical section, and if I have P1, right, so here, just a second. So let's suppose no process in the critical section, and let's suppose some turn is initially 0, and then P1 arrives. Can P1 enter in the critical section? No, right? So since it cannot enter in the critical section, that's why I will say that that the turn, I mean, because of this turn variable, the progress is not satisfied, right? Okay, I hope everyone understood. Now let's just move further. So progress is not satisfied. Yeah, progress not satisfied, right? Okay, let's see this question. In this question, what we are saying, it is also a two process solution, and we want to check whether the progress is satisfied, whether the bounded waiting is satisfied, or like that, right? So let's suppose that this want is one variable which is which is having initially 0 and 0. Tell me if mutual exclusion is satisfied. To check mutual exclusion, what you will do? Let's check if one of the process in the critical section, which means initially this bound is initially 0 0. If one of the process, let's suppose this is in the critical section, then this will make it 1, and then want 1 is false, so it will come out of the loop. And let's suppose this P naught is in the critical section, and currently this is the situation of the want, which means want 0 is 1, and then this value is 0. Now tell me, can P1 enter? If one of the process in the critical section, can another process enter? Can P1 enter? This want 1, it will make it true, and then since want 0 is 1, that's why it will get stuck here, right? P1 cannot enter. So I can say, while P naught is in the critical section, P naught cannot enter. That is the one thing to check for the mutual exclusion. Second thing is that what you will be checking, you will be checking if two processes wants to enter, right, at the same time, then at most one should be allowed, right? Let's suppose two processes wants to enter at the same time. Okay, so want 0 equal to 1, then want 1 equal to 1, then both will get it, both will get stuck. That's okay, I mean, that's perfectly fine for me. For mutual exclusion does not say that always allow one, so both will get stuck. That's why mutual exclusion is satisfied. Since there is a deadlock condition, that's why progress is not satisfied. And what about the bounded waiting? You can check easily, right, if bounded waiting is satisfied or not. You make one of the processes in the critical section, maybe P naught, and then check if you can bypass. Can you bypass? I think want 0 equal to 0, I think you can easily bypass, right? So that's why bounded waiting is also not satisfied. Okay, so I hope that is fine to everyone. Let me know if there is any doubt. Okay, so moving further. Now let's take some of the gate question so that you can have a good practice. Let's take this gate question. What this question is saying, that consider the methods used by the processes P1 and P2 for accessing their critical sections whenever needed as given below. So this is the method for P1, this is the method for P2, and then which of the following statement describe the properties achieved while S1 equal to S2. Okay, let's just check this. Let me just go to the next page, maybe. So first you can take initially you can take any of the value of S1 S2 if it is not given. Whatever is the value, I mean, S1 S2 can take total 4 possible values, 0 1 1 0 1 1. Whatever is the value, let's just boils down to the two conditions, whether S1 is equal to S2 or S1 is not equal to S2, right? Let's suppose if S1 is equal to S2, then this condition is true, and then let's suppose P1 wants to enter. Then can P1 enter? Since P1 cannot enter, that's why you will say progress is not satisfied. So progress says that if some of the process wants to enter, okay, irrespective of anything, then it should get enter. I mean, if P2 is not there at all in the picture, P1 wants to enter, then P1 should get enter, right? So that's why the progress is not satisfied, because P1 is not able to enter. What about the bounded waiting? And what about the mutual exclusion? See, mutual exclusion seems satisfied because either this will be false. I mean, either you will say S1 equal to S2 or S1 not equal to S2. Based on that, one of them will get stuck, one of them will get passed, right? If both the process wants to enter at the same time. So that's the first thing for the mutual exclusion. Second thing is that you make one of the process in the critical section and check if another one can enter. Since one cannot enter, that's why mutual exclusion is satisfied, right? What about bounded waiting? So let's suppose this process is here, and now let's just check if you can allow other process. If this process is here, it means S1 must not be equal to S2, right? S1 must not be equal to S2, which means this is waiting. Then can it go out S1 equal to S2, and then can it come again? It cannot come again, right? Because S1 equal to S2, so that's why this condition will be true. It cannot come again. So you will say mutual exclusion and bounded waiting both are satisfied, but progress is not satisfied. Okay, they have not asked for the bounded waiting, but yeah, mutual exclusion and mutual exclusion is satisfied, but progress not. So A should be the answer, right? Yeah, A is the correct answer. Okay. So let me know if that is clear to everyone. Yes, Vikram. No progress. Okay, moving further. So let's solve this question. This question has been asked in GATE 2007. Let's solve this question. Let me do one thing. Let me just copy this question on the probably next slide. Okay. Just to avoid the confusion, this while true I'm just removing because it is just saying that it will keep on happening again and again. This while true I'm removing. I mean, this is not just helping us, so that's why I'm just removing it, right? Okay, now let's solve this question. And instead of writing wants to equal true, can I just write it wants to? I mean, you can say wants to equal to true also, or you can just write wants to, right? Something like this also. Similarly, instead of writing wants one equal to true, you can just write wants one. Okay. So this is the question that they have. Let's just solve this question now. So what they are asking is that they are saying it does not ensure mutual exclusion, bounded waiting, progress. They are asking about the three things, right? Okay, it does not prevent deadlock. So let's just check mutual exclusion is there or not. So initially, what is the value of wants one and wants two? They have not given the initial value, or they have given. Yeah, both are given to be false. So initially, both are given to be false. So this wants one is equal to false. Wants two equal to also false. Now let's just check mutual exclusion is satisfied or not. How to check mutual exclusion? There are two things. Let's just check if both the processes can enter at the same time. So obviously it will be a deadlock, right? So there's a deadlock condition. Deadlock is there. So I mean that's fine. The mutual exclusion is satisfied as long as I can see, because if both the process enters at the same time, they cannot enter. Both are stuck in the deadlock. So can I say mutual exclusion is satisfied just by looking at it? Let me know. Can I say mutual exclusion is satisfied just by looking at it? I mean, maybe satisfied, may not be satisfied, but just using this kind of analysis, can I say mutual exclusion is satisfied? No. Reason being is that there are two things that I want to check for the mutual exclusion, not just one thing. Okay, I do not only check whether both process wants to enter, then can they enter. Second thing I check. Okay, let's suppose this process is in the critical section, right? Let's suppose this is in the critical section, which means that wants one. Okay, it is in critical section. It must mean that wants one is true and wants two must be false. Now in this case, tell me, can another process enter? No, right? I mean, if another process wants to enter, wants to, it will make it true, but wants one is also true, that's why it will get stuck. So that's why I will say mutual exclusion is satisfied. Right? Let me know if there is any doubt till this point. See, I need to check two things for the mutual exclusion. I'm just checking both of the things, and based on that, we are just concluding whether the mutual exclusion is satisfied or not, right? Okay. Let's move further. Now, tell me if the progress is satisfied. I'm sorry. So they are asking about the bounded waiting and progress. So tell me if the bounded waiting is satisfied. Since the deadlock is there, so that's why you can say progress is not satisfied, right? I mean deadlock is there, so how can progress be satisfied? And tell me now, bounded waiting is satisfied or not? What does bounded waiting says? Let's suppose this process is here. Can this go out? Then once one will be false. Can this go out and can this go again in? While other process is here, other process is here means wants two must be true, and then it is waiting, right? Now tell me, can it go out? Then it will be false. Then once okay, once one again true. Then since once two is true, it cannot come again. That's why bounded waiting is satisfied, right? So mutual exclusion is satisfied, bounded waiting is satisfied, progress is not satisfied because of deadlock. It does not ensure mutual exclusion, no, it ensures. It does not ensure bounded waiting, no, it ensures. It requires that processes enter in the critical section in strict alternation, which means one after another. Let's just check this. It does not prevent a deadlock, but ensures the mutual exclusion. Yes, that seems true, right? It does not prevent deadlock, but ensures the mutual exclusion. Let's just check if C is true or false. We have not checked for the strict alternation, right? So D is the correct choice, but let's just check if C is true or not. Let me know if everyone is with me till this point. So in C, I want to check whether the strict alternation is there or not. So for that, what will I do? I will check. Okay, let's suppose maybe P1 is not at all interested, right? Is not at all in picture. And initially, let's suppose that I have both of them as false. Okay. If both of them are false, then it will make it true. It is false, it will go here, and then it will make it false. Then again it can go, right? Again it can go. Yes, it can definitely go again and again. So basically, which means, yeah, that's very interesting. It means that if P1, okay, this is P1, which is not in the picture at all. In this case, there is no strict alternation. I mean, I'm not saying that after P0, P1 will always be there. No, P1 can go again and again, right? But does this mean that bounded waiting is not satisfied? No. For the bounded waiting, I should be making P1 wait here, right? I should not be saying that P1 is not in the picture, right? I should not be saying this. To check the bounded waiting, I should be making the P1 wait here and then P0 here. Then I should be checking whether the P0 can enter again. That's the process of the bounded waiting. Okay. I hope everyone understood this, right? Great. Now let's move further. Let's solve this question which has been asked in GATE 1998. They are saying given below is the solution for the critical section problem of two processes P0 and P1 sharing these variables. So flag is one variable that is being shared. I think this is an array, right? And initially the value is false. So flag 0, this is false, and this is also false, right? The program below, which is having the like P0 and P1 being other one, right? Okay, determine if the above solution is correct. If it is incorrect, so let's just check if the mutual exclusion and these things are satisfied or not. So let me do one thing. Since they have given this to us, they are saying that the program below is for PI, for a general process PI. Now let me write a program for P0 and P1. So for P0, how it will look like, for P1, how it will look like, right? So for P0, what will I do? Instead of I will be making 0. Instead of j, I will be making 1, right? Something like this. I think I do have that on the next page. So yeah, for P0, instead of I will be making 0, and instead of j, I will be making 1, right? So this is the code for P0, this is the code for P1. That is given to us, right? There is nothing I did. This is clearly given to us. Let me know if that is fine. Okay, now let's just check if the mutual exclusion and these things are satisfied or not. So how you will be checking? I mean, that's a very easy way to check, and they have initially given both of them to be false, right? So flag is initially, which is a shared variable. Okay, so initially it is false, and then turn is also turn can take 0 and 1, and they have not specified what is the initial value of turn. So you can take anything, right? So this is the flag. They have specified the initial values of the flag, but turn initial value is not specified to us. You can take anything. Let's take 0 or 1, does not matter. So let's just check if mutual exclusion is satisfied or not here. How you will be checking? See, like, do you want to spend 1 minute before I solve this question? Maybe you can just check for 1 minute and then I will solve this question, right? Just check if mutual exclusion is satisfied here or not. And let me know what you are getting. See, let's just check it. So currently, what do I have? What I need to check for the mutual exclusion? I will be checking. Let's suppose one of the process in the critical section. Let's suppose that this process, which is P note, is in the critical section, and P1 wants to enter. So if this P note is in the critical section, then can you tell me what should be the configuration? Which means if P note is in the critical section, then what will these values? This must have been true, right? If turn is not equal to 0, so turn must be 0. If turn is not equal to 0, then I think this is just in the loop or something. Then turn must be 0, right? Because this is false. Okay, turn because okay, turn is not 0, then they will make this turn 0, because this will make this turn 0. Okay, cool. Now, this is the current configuration. Now check if this process wants to enter, then can it enter? The flag one, it will make this true. Turn is not equal to 1. Yeah, that is true. So it will get stuck actually here, right? If turn is, okay, turn is not equal to 1, it means, sorry, this is the curly braces. Do begin end means these are the curly braces I have. If turn is not equal to 1, which is in fact true, so it will check whether the flag is basically checking whether the some other process is interested or not. Flag is basically the interest. It will first check, okay, it is not my turn is not equal to 1, it means it is not my turn. Then I will check whether if someone else is interested. Yes, someone else is interested, so I will be keep on waiting, right? I will keep on waiting. So you cannot enter both the process at the same time. That's why you will say the mutual exclusion seems satisfied here, right? But if both of the process wants to enter at the same time, then can they enter? They will make both of them as true. Then one of them is true and one of them is false, right? Since turn is either 0 or 1, based on that it will come here. So that's why you will say that both of them cannot enter at the same time. So that's why this mutual exclusion is satisfied here, right? Okay, see here what is the answer they are giving. The above situation satisfy the mutual exclusion and progress and violates the boundary betting. So anyway, the mutual exclusion is satisfied here. Now let's just check if progress is satisfied. Progress means that if two processes, okay, entering at the same time, then like that's the one thing that you need to check. Then it should allow it should allow at least one of the process, right? It should allow at least one of the process. And second thing is that, like, I mean, how you can check? Let's suppose if in whatever is the initial configuration, okay, turn could be 0 or 1, then let's suppose P node wants to enter initially, okay. So suppose I want to check for the progress. So this turn could be 0 or 1, anything. And let's suppose if P node wants to enter. If P node wants to enter, can it enter? Turn is not equal to 0. So that is actually false. So it can enter, right? And what about P1? Turn is not equal to 1. That is true. It will check whether the flag 0 is actually unset, which is false. So this will not get stuck here and it will actually enter. So if P node wants to enter or P1 wants to enter, they can enter, right? So for the progress, you need to check two things. Do you remember? See, for the progress, you need to check two things. What are those two things? These are the things that we need to check. no process in the critical section and P1 arrives, then it should be allowed. If two or more processes are in the waiting area, then at least one should get enter, right? So which means there is no deadlock actually. So yeah, here first condition I have checked. Now let's just check second condition. If two processes wants to enter at the same time, then it will say that it is true, it is true. Turn is, let's suppose, 0, then one of them will get enter, right? Based on that turn is 0 or 1. So yes, one of them will always get enter. So that's why progress is satisfied. Now let's just check if bounded waiting is satisfied or not. Okay. So let me know if everything is fine till this point. Okay. So someone is having some doubt. Sir, please explain the case when one process in the critical section, another is stuck in a loop, then bounded waiting is possible or not. If another is stuck in the loop, one process in the critical section, then another is stuck in the loop, and then you have to check whether it can bypass the process or not. I think we have just explained it here, right? So one process in the critical section, another one is waiting, then we need to check whether it can bypass or not. Since it was not able to bypass, so that's why the bounded waiting is satisfied here. Having a doubt in bounded waiting, what do you mean by the passing of other process? See, I think there is some doubt in bounded waiting. Bounded waiting is extremely easy to check. You just make one of the process in the critical section and another process in the waiting area. Okay, so just make one of the process in the critical section, another process in the waiting area, and at that time check if you can re-enter. So let me just solve this question again probably. So see here, wants are initially are false. Okay, let's suppose wants are initially false. I want to check for the bounded waiting, suppose. Okay, so want one is false initially. Let's suppose this is given to us. Now let's just check if bounded waiting is satisfied or not. For the bounded waiting, what you need to do, make one of the process in the critical section. To make one of the process in the critical section, you need to make it true because it will be executing this, and then it is false, so it is in the critical section. Now make one of the process in the entry section, waiting in the entry section here, which means P2 is here. If P2 is here, then it must also be true now, right? Okay, this is the initial setup for the bounded waiting. Okay, or P2 or P0, P1, whatever you want to say. This is the initial setup for the bounded waiting. Now what you need to check, very simple, just check if P0 can exit, which means it will make it false, and can re-enter, it will make it true, and then it will execute this wants to. Since wants to is true, it will get stuck here. It cannot exit and re-enter. Since it cannot exit and re-enter, that's why bounded waiting is also satisfied, right? So bounded waiting is very easy to check. You just make one of the process in the critical section, another process in the waiting area, and then just check if this process can go and re-enter. That's all. So let's just have the bounded waiting case for this example. Let's just check if bounded waiting is satisfied here or not, right? So I will say progress is satisfied. Let's just check for the bounded waiting. So initially, let's suppose turn is 0. Okay, I mean the turn initial value is not given, so you can try with the other values also. And flag initial values are given, which is false and false. Flag is generally, basically, if there are two variables, flag and turn. If turn is very obvious, then another variable is generally interested, which means it just shows that if someone is interested or not. Okay, anyway, now let's just check if bounded waiting is satisfied or not. You just make one of the process in the critical section. Okay, this process in the critical section, P0 in the critical section, which means this must be true and turn is not 0, right? Okay, turn is not 0. 0 is not, I mean turn is actually 0, so that's why it will be false. So that, I mean, things are fine. So which means this process is here. Make another process in the waiting area. So here the waiting area, so do begin means, I mean this is actually just like a while loop, opening parenthesis, closing parenthesis. Okay, so make another process in the waiting area. Here the waiting area is this. So if the P1 is here, then it means that flag 1 must be true, right? And then turn is not equal to 1. Turn is not equal to 1. Turn is 0, which is, I mean this is actually not equal to 1. So this is true. It will come inside this while loop, and then it will check the flag 0. Flag 0 is actually true, so it will get stuck. So currently this is the base setup for the bounded waiting to check the bounded waiting. I made one of the process in the critical section. I made another process in the waiting area. Let me know if the setup is clear to everyone. Okay. Is setup clear to everyone? So let's just understand with this help of this example. If setup is clear, which means I'm making one of the process in the critical section, another process, then I make another process in the waiting area. Okay. Now let's just check if this process can go out, which means it will make flag 0 false, and then again it will make true, and then can go in again. Turn not equal to 0, turn value is actually 0, so that is false, right? That is false. It can go again, right? It can re-enter. Since it can re-enter, that's why bounded waiting is not satisfied. Bounded waiting is actually very easy to check. You just make one of the process in the critical section, another process you make in the waiting area, and then just check whether this process that you made in the critical section can re-enter, right? Okay, so that's why you will say bounded waiting is not satisfied, but it violates the bounded waiting. Great. Now let's just move further. Let's just solve this question. This question has been asked in GATE 2015. Okay, what this question is saying, let's just see. So two processes X and Y in the critical section, consider the following synchronization construct used by the processes X and Y. Now they are saying the process propose the solution prevents the deadlock but fails the mutual exclusion, something like this. So they are asking about the mutual exclusion and deadlock. Let me do one thing. Let me just copy this on the next page, and let's just check if I can check about the mutual exclusion and deadlock they're asking. Okay, so okay, let me just remove some of the unnecessary line which might not help us. Cool. Now let's just check if mutual exclusion is satisfied or not. So here, this to check the mutual exclusion, what we need to do? We need to check if both the processes can enter at the same time. So var p equal to true, var q equal to true. I think since var q is true, it can enter. Since var p is true, it can also enter, right? So I think both the processes can enter at the same time. So that's why mutual exclusion is not satisfied here. Is this okay to everyone? Now for the progress, what you need to check? Let's just check if what you need to check? Okay, deadlock. Can there be a deadlock? Tell me, can there be a deadlock? Deadlock means it should get stuck, but I don't even see any infinite loop here. Right? Since there is no infinite loop, I mean, it is not having any infinite loop which is waiting. So that's why deadlock is not possible here. See, there is no infinite loop. Infinite loop means that it is keep on waiting, keep on waiting, keep on waiting. Since that's not the case, so that's why I will say, okay, no, I cannot argue something like this, because originally this is while 1. I mean, originally it was while 1 and it was something like this, right? So maybe if it is false, again and again, then I can be in the infinite loop. So anyway, let's just check if the progress is there or not. So for the progress, what you need to do? You check if both processes wants to enter. Can both enter at the same time? If both process wants to enter, then yes, both can enter. So for the progress, we check two things. If both process wants to enter, can both enter? Second thing is that, do you recall the second thing? Can anyone tell me what is the second thing? See, for the progress, there are two things that you need to check. Let me just recall you. If two or more processes are in the entry code, show that at least one will enter, right? And another one is that if someone is not interested, then P1 arrives, P1 should get enter. So let's just check the first criteria, which means if let's suppose that this is not even interested, and this comes var q equal to true, and what is the var q initial value, shared value, both are initialized to false. Okay, so var p is false initially, var p q is also false. Now suppose this is not even interested, this is interested, it will make it to true. Since this is false, right? It is not true, it will not get enter. So is progress satisfied here? No, right? Progress is not satisfied, because if this process is not at all interested, then this process cannot enter in the critical section. See, originally this was the while one, right? So it will keep on looping here. It will say, this is true, this, since this is not true, it will loop again, it will loop again, right? So the progress is not satisfied here. You will say progress is not satisfied. Is there a deadlock? Tell me, is this a deadlock? So mutual exclusion is not satisfied, but progress is also not satisfied, right? But progress is actually having the two things. Okay, see here, progress is having two criterias. The second criteria is same as actually deadlock. I mean, if no process in the critical P1 enters, P1 should get entered. This is the first criteria. So if you remember, I told you that there is a little difference between progress and deadlock. So progress is a superset of deadlock, right? So here progress is not satisfied, because if P1 wants to enter, P1 is not able to enter. P2 is deciding whether P1 can enter or not, right? So that's why the progress is not satisfied. But the second thing is says that if two or more processes in the critical section show that at least one should enter, so this is checking the deadlock basically. Since at least checking deadlock, this is same as actually deadlock. Okay. So since at least one can enter here, that's why the deadlock is not there. If two or more processes are in the intersection, see, if two or more processes are in the intersection, which means it wants to enter, it also wants to enter. Both can enter. That's why the deadlock is not there. For deadlock, you need to check if there could be the infinite loop. I mean, if everyone is waiting for every other one, which means if both process wants to enter, then they should be waiting for each other. Okay, so see here, the progress second condition is basically same as deadlock. The first condition is saying that no process in the critical section, if P1 arrives, then P1 should get enter. So this is a very good example where you can see the difference between the progress and deadlock also, right? So here the progress is not satisfied. It does not mean, it does not mean that deadlock is also deadlock is not there. Okay. So deadlock is not there. Deadlock is also not there. Progress is not there, deadlock is also not there. Because of the first condition, progress says that if both wants to enter, then they should not be waiting for each other. Since they are not waiting for each other, that's why deadlock is not there. But progress has one more condition. It says that if this wants to enter, right? Initially, let's suppose this only wants to enter, and this is not even interested. This process is not even interested, and only this wants to enter. Then in this case, you will say that this cannot enter because var q is initially false. Since it is false, it cannot enter here. That's why the progress is not satisfied. Okay. Let me know if that is fine to everyone. See, no progress does not always mean the deadlock. If you remember, I said that I will clarify this. So no progress does not always mean the deadlock. So progress is not there because of the first condition here. That's why like progress, the deadlock is actually not there. In this case, progress is not there, and deadlock is also not there. In this case, deadlock is also not there, because deadlock is not there. Like progress is basically a superset of deadlock, right? So progress is having two conditions. One is if no one is interested, and someone wants to enter. This is first condition in case of progress. Second one is that, okay, so second condition says no deadlock. So basically progress is having two conditions, and just because there is no deadlock, you cannot say there is no progress. I mean, there is no deadlock, then progress is there. Sorry, progress is there. Maybe this condition fails. So this is the example where this condition is failing and this condition is passing, which means that if someone wants to enter suddenly, I'm not allowing it, right? If this is not interested, if this wants to enter suddenly, I'm not allowing it. That's why progress is not there. But deadlock is also not there here. Okay, let me know if that is okay to everyone. So progress is actually a superset of deadlock, right? So here the answer is A. A means the proposed solution prevents the deadlock. There is no deadlock but fails to guarantee the mutual exclusion. Okay, I hope that is fine to everyone. So there is no deadlock because it prevents the deadlock, but the mutual exclusion is not satisfied. So how to check deadlock? Can anyone tell me how to check deadlock? You just check if both the processes are interested at the same time. Then are these two processes are stuck in each other, right? That's how you will be checking the deadlock, which is one of the condition of the progress. Okay. Now let's just solve this question, and then we will move to the semaphores. So what this question is saying, they're saying I think the same thing. Consider the two process synchronization. They are asking this is correct synchronization, mutual exclusion, progress, boundary waiting. So they're asking about the these three conditions only. So let me just take this question. Let me go to the next page. Okay. So here, what is the initial value of turn? The shared value of turn is initialized to 0. Okay, turn is initially 0. Tell me if progress is there. See, that's very easy example to check progress. See, one of the process will get stuck, right? If this wants to enter, maybe 0 is equal 1, so okay, this is false, so this will be allowed. But if this wants to enter, this will not be allowed. So definitely the progress is not there. I mean, the first condition is not satisfied, so that's why progress is not there, right? Now let's just check if mutual exclusion is there. How to check mutual exclusion? Take both the processes and check if both the processes enter at the same time. Since both of them cannot enter at the same time, that's why it seems that mutual exclusion is satisfied. But I do have to check one more thing. Make one of the processes in the critical section, which means turn is initially 0. So that's why it is in the critical section. And then check if another one can enter. So since another one cannot enter, that's why mutual exclusion is satisfied. What about the bounded waiting? Bounded waiting is also very easy. How to check? Make one of the process in the critical section here, which means turn is initially 0, and this will be the critical section. Make this here, which is P1 is here, and now just check if this can go, which means it will make the turn 1 and then can re-enter. It cannot re-enter because turn is 1, it will get stuck. So that's why bounded waiting is also satisfied, right? So what is the answer? This solution violates the progress. Progress is not there, mutual exclusion and bounded waiting are there, right? So that's why C is the correct answer. Let me know if you understood this thing. I hope that is fine to everyone. That how to check for these three conditions is very crucial. Like for progress, we need to check two things. Similarly, for mutual exclusion, generally this mutual exclusion is easy, but still let's just take care of the two things. Whether, just do one approach. Just first check whether both the process trying to enter at the same time. Just check this. Trying to enter at the same time. Then check how many you can allow. Okay, if the both of the process wants to enter at the same time, then just check if you are allowing 0. I mean, if you are allowing 2, then mutual exclusion is not there. If you are allowing, okay, if you are allowing 0, or maybe then if you are allowing 0, then progress is not there. If there is a deadlock, and if you are allowing exactly 1, then both are there. So first thing is that just check just before checking for this mutual exclusion, progress and bounded waiting, first thing you do is check if both the process want to insert at the same time, what is happening. Okay, and then based on this you will filter out that whether something is not there, something is there or not, that you have to check with one more criteria. See, mutual exclusion, for checking mutual exclusion there are two criteria, right? For progress also there are two criteria. For bounded weighting there is just one thing that you need to check. Now like these two criteria are also almost same, which means if both the process wants to interact at the same time, then what happens, right? If both wants at same time, so these two are same. So that's why just check if both wants at the same time, then what going to happen? That's the first thing, just do it. Okay, that will tell you if mutual exclusion is not there. I mean, it will not tell you if it is there, because for there you have to check both the condition. It can just tell you if something is not there. If it is not there, okay, it will just tell you something is not there, right? And then what you need to do, I mean, once you do this, then you need to check for the mutual exclusion, make one of them in the critical section, check if you can allow other process, right? For progress, just check if arbitrarily some processes wants to enter, then it can enter. For boundary bitting, you know what to do, right? I mean, make one of the process in the critical section, another in the waiting area, and then you can check for the bounded waiting. Okay, I hope you understood this. Let me know if there is any doubt in this. Now I think it is good time to see the semaphores. So now let's just see the solutions using the semaphore, right? So before that, let me know if there is any doubt till this point, and then we will check the semaphores. I mean, it is easy. Just with the practice, you will get to know it more, maybe, right? Should we do the semaphore now, or can we do it later? Maybe in another session. So let's just do one thing. Maybe we can follow the semaphore in another session, right? Okay. So I'm terminating this session. We will schedule another session to just continue the semaphore. Thank you everyone. Let me know if there is any doubt to anyone. So we are following one schedule to for this revision session, and we will be covering almost every concept that is necessary for you to revise, and that is necessary, that is crucial. So basically what you can do, you can find the complete schedule at the link. Okay, I will share the link in the description section, and also let me just give you some partial screenshot that how we are following the sessions. So see here, if you can see my screen, that this is how we are basically conducting the sessions, right? I mean, there is a fixed schedule on which we are conducting the sessions. Thank you everyone. Take care. Bye bye. If there is any problem, let me know.